So before starting to talk about the Bode plot in a traditional manner, let us first try to uh, qualitatively analyze, because we are interested in the frequency analysis and to know the output for the whole frequency spectrum when we perform frequency domain analysis, of which Bode plot is an approach of. So in fact, Bode plot allows the frequency information to be displayed graphically on two different plots. One is called the gain plot or the magnitude plot, the other is phase plot. So if you see at the bottom of the slide, you'll see that there are two boxes. One will be going, we are going to, in one of the box will be representing the magnitude plot, and in the other box will be representing the phase plot. Since we learned in frequency analysis that whenever we are going to feed a sinusoidal waveform to a LTI system, then the output will also be a sinusoid. And on changing the frequency of the input, so if you're going to change the frequency of this input, then you will observe that the output from the system will be having the same frequency. The only thing that is going to change in the output waveform will be the change in the amplitude as well as phase. And we are interested to plot the change in the magnitude and phase of the output for different values of frequency. So the concept of Bode plot can be understood by the given block representation, where we are trying to just hypothesize the concept of Bode plot by connecting a sine wave generator that is capable of generating frequency from 0 to infinite. So these are something. This is something just mere to explain the concept of Bode plot. And the sine wave generator will be producing the sine waves of a fixed amplitude but varying frequency, which will be fed to the control system. And the output of the control system will be studied for different frequencies, and the magnitude and phase will be plotted for different frequencies. So we'll observe that when we vary this frequency from 0 to infinite, then there will be a change. So we are going to change the frequency of the input waveform, and we are going to observe the changes in the amplitude and phase of the output waveform that will be drawn on these two plots. So when we vary this frequency from 0 to infinite, we'll observe that the magnitude behavior and the phase behavior of the output waveform will be having a pattern. So we are going to collectively refer these two plots as Bode plots. So in Bode plot, the study of frequency response, the magnitude GJ omega and the phase angle GJ omega is analyzed by varying frequency from 0 to infinite. So this is common to all the frequency response methods that we'll be learning, or that comes under the Unit 4. And this variation in essence can be represented on two graphs, namely gain plot, which is magnitude of GJ omega in decibels versus omega, and the phase plot phi versus omega. These two plots are collectively called Bode plots. The magnitude is expressed in decibels unit, given as magnitude GJ omega in decibel is 20 log of 10 to the base 10 magnitude GJ omega. So in order to find the magnitude in decibels, you will be first computing the magnitude of GJ omega, and then you will be taking the 20 log to the base 10 of that magnitude in order to obtain the magnitude in terms of decibels. The phase is expressed in degrees and frequency in radians per second. Bode plots are constructed by using straight line approximations. So what does that mean? So since Bode plots that we will be drawing by hands are approximated plots, so not exact. So in order to obtain the exact plots, very similar to root locus. So in case of root locus, what we did was we by hand were drawing approximate plots. While if you require exact plots, then you will be using simulation softwares like MATLAB. So by using straight line approximations that are asymptotic to the actual plots, which means that if you draw the Bode plot by hand, so you'll be obtaining straight line approximations, or you'll be obtaining straight lines. which are nothing but the asymptotes to the actual plot if you draw those actual plots using softwares like MATLAB. The Bode plot has the following features. Number one is that while operating in decibels, product and division factors in G omega become addition and subtractions. So that is clear because you are dealing decibels in log scale, mathematically in log form, and thus any product will be changed into terms which are added, and any terms which will be divided, when you take log of them, they will be subtracted. So this is because of using log. The magnitude plot of Bode plot of G omega can be approximated by straight line segments. So this is something that we discussed at the top point, which allows the simple sketching of the plot without detailed computations. So in fact, whenever you try to conclude about the behavior of any system or the stability or relative stability of the system, Bode plot drawn by the approximate Bode plots are enough to conclude about these. Bode plot are one of the widely used methods to perform frequency domain analysis of systems. So it's one of the methods that is preferably used in industries in order to understand the frequency analysis and stability or relative stability of systems. Semi-log paper, unlike log-log paper. So in order to draw the Bode plots, you will be using a graph paper called a semi-log paper. So it is a bit different from the normal graph papers. And then you again have log-log papers. So while Bode plots are drawn on semi-log papers, there exist log-log papers as well. So I'll explain, you can easily remember by their names as well, that semi-log or half-log paper stands for papers that will be having one scale in log form or in log scale, and the other scale will be linear. While in case of log-log paper, you have both the XY scales in the form of log scales. So unlike log-log paper has one axis on logarithmic scale and the other on linear scale. So we're talking about semi-log paper. Bode plot are drawn on semi-log paper. Omega is drawn on axis corresponding to the log scale, while magnitude and phase are drawn on linear scales. So if you see this plot, so we see that the marking on the x-axis, the frequency axis, which is omega, which represents omega. So you will see that the marking is unusual. It's not linear. So you have divisions. For example, after this particular division, you have another division here. Then the other division is not uniformly distributed from, is not at a uniform distance as the first point. So you'll see that there is no uniform distribution in the scale. So in fact, this is because of taking the scale in log form. So we'll discuss this in detail in the log in the next slide. While on the y-axis, you will see that there exists a linear scale. So in Bode plot, what we do is we will be plotting on y-axis, we'll be taking linear scales for marking phase and magnitude, while on x-axis we'll be taking the logarithmic scale, and that will be representing omega or frequency in radians per second. So this is what it means. Bode plot are drawn on semi-log paper. Omega is drawn on axis corresponding to the log scale, which is x-axis, while magnitude and phase are drawn on linear scales. Now this is the actual semi-log paper that you will be normally working with, and you can easily find this on stationery shop. So if you look into this paper, you'll find that you have scales at the x-axis which are not linear or not uniformly distributed, as I just told you. And if you look at the top side of this graph paper, there are certain marking like 1, 2, 3, 4, 5, 6 up till 10. Then again you have starting from 10, 1, 2, 3, 4, 5, again 10. So this, in fact, the x-axis is a representation of logarithmic scale on paper, which means that if you suppose start from actually from 1, then this point correspond to 10. If this had been a linear scale, then if you're going to identify the first point as omega 1, so if you say that the frequency of this point is 1 radians per second, then the frequency at this point will be omega as 10 radians per second. And following this, if you take this point as reference, the marking shown on the graph paper is 1, then 10 here, then again 10 here. But after you take the first point as reference, for example, omega equal to 1, then this point will be taken as omega equal to 10, and this will be taken as omega equal to 100. This becomes omega equal to 100, and this becomes omega equal to 1000. Since you are trying to plot the values of omega in the form of log scales, so if you convert, for example, 100 by taking log to the base 10 of 100, what you get is 2, and log to the base 10. So for this point, if you talk about the log values, then log to the base 10 of omega here is 10. So this is 1, and this is 2, and this is 3. So this is where we get the term decades from. So 1 decade stands for the gap that exists between these 2 points. So if you talk about the reference starting from this point as omega equal to 1, then this becomes 1 decade, and from this point this becomes 2 decade, and this becomes 3 decades. So you will be writing, when you try to obtain the Bode plot, you will be writing in terms of decades on x-axis, but by those decades, in fact, you will be assigning omega as 1, 10, 100, 1000. So these values are in radians per second, though the graph is in decades. And in case of linear scale, we will study that we are going to obtain dB, decibel, and we'll be plotting this log on linear scale. So they, in fact, on y-axis you have a different sense of drawing, and then on x-axis you have a different sense of drawing. So if you try to focus things out, if you try to understand, if you try to study this, you will come to know what the difference that exists between x-axis and y-axis. So the main point is that on x-axis you have omega represented linear, 1, 10, 100, 1000, but the scale is logarithmic. While on y-axis you have scale linear, but the representation is in dB, which is logarithmic. In fact, 20 log to the base 10. So you'll have to try to think over it to understand the difference, and if you feel problem, you can ask me. Then we define a term as decade, which is nothing but the ratio of the frequency omega 2 to omega 1, and will be equal to 10. So this gap from omega 1 to omega 2 is 1 decade, and from this point to this point you have 2 decades. Then again, if you talk about this difference or this gap, this becomes 3 decade. So it means that the points that you have on the log scale So this particular point and this point, the gap between these 2 points is a decade. Likewise, between this point and this point is again a decade. So we normally measure the graph on the log paper in the form of decades. So we define this instead of centimeters as decade. Likewise, on the y-axis, since you have linear scales, you have divisions of 1 centimeter or 1 millimeter. So for example, if you look for the small boxes, the small blocks, they are 1 millimeter apart. If you count for the blocks, so the 10 divisions will correspond to 1 centimeter. So this is the semi-log paper that you normally employ for plotting Bode plots, and here is a link from where you can download this graph paper. Now we start with an example of plotting the Bode plot of 1 upon s. So this is the simplest form of any transfer function that we will be drawing a Bode plot for. So consider a system with transfer function g equal to 1 upon s, the frequency response function. So frequency response functions mean that we will be replacing s by j omega, and that is obtained by substituting s equal to j omega, that is g j omega will be equal to 1 upon j omega. Now we'll be computing magnitude. So if you remember that what we try to do in every frequency domain analysis. So this is the general rule or the procedure that we learn will be applied for any frequency domain approach when we try to analyze systems. So you will be having all these the first three steps common in all the approaches. So you will be first replacing S by G omega in order to obtain the frequency response frequency function. And the second step says to obtain the magnitude of the obtained frequency function and the phase. The third says to obtain the phase of the frequency function that you obtain. So the same thing we are going to apply for the Bode plot. So the first three steps will be common, and thus we obtain the frequency response function. Then we obtain the magnitude by taking by applying the second step. So the magnitude of G will be 1 upon omega, and from this we can easily obtain the magnitude in decibel. So in decibel we compute the magnitude by taking the 20 log to the base 10 of the magnitude Gg omega, and this gives minus 20 log of omega to the base 10. So since you have this magnitude as 1 upon omega, and omega, if you're going to take reciprocal, will be giving you omega to the power minus 1, and that minus 1 will multiply with 20. So this is the magnitude in decibels of the transfer function 1 upon S. Which means that if you are going to substitute the value of omega, different values of omega, for example omega equal to 1, in that case you are going to get decibel in as 0. If you substitute omega as 10, then the magnitude in decibels will be minus 20. If you substitute omega as 100, the decibels from this expression, if you're going to substitute omega as 100, so log to the base 10 of 100 will be 2, and multiplied by minus 20 will give you minus 40. So likewise you can obtain more values for different values of omega, and we are interested because we saw that we have to plot magnitude versus omega and phase angle versus omega. So we will be plotting decibels versus omega for different values of omega, and since these are approximate plots, and that is why we are obtaining different values of or different points on the graph for different values of omega. Now in continuation, for each 10-fold increase in angular frequency, the magnitude drops by 20 dB. So this is what we saw. For a 10-fold increase in frequency, the magnitude drops by 20 dB. Thus the magnitude plot for this is a straight line with slope minus 20 dB per decade, and it passes through 0 dB at omega equal to 1 radian per second. Now we come with a new term, which is slope of dB per decade. So what and how do you identify slope? So if you remember in normal graph paper, you have marking on the x-axis as well as y-axis in centimeters. So if this is x-axis and this is y-axis, you have marking in centimeters on both the axes. And you say that, so let's first write this as centimeter. If you are interested in plotting a slope of, let's say, 1, so this means that this represents 1 centimeter by 1 centimeter, y is to x, the slope of 1. So slope, if we talk about slope equal to 1, so this is a line that will be passing through points like 1, 1 or 2, 2 or 3, 3. So you'll be having this straight line which will be having slope as 1 or 1 centimeter by centimeter. So the slope will be 1 centimeter by centimeter, and we normally do not prefer writing slope in this form. We simply represent this as 1, 2, 5, minus 1, minus 10 like this. So we normally do not write in the form of centimeter by centimeter. So likewise, if somebody wants to draw a slope of 2, So in that case, what and how you draw a line having slope of 2 is you are going to take two parts of y and one part of x. So slope, if you talk about slope, equal to 2. In this case, you will be having two parts of y. So two parts of y means this point, and one part of x. So you have this point. So a straight line passing through 0 and this particular point will be having slope 2. So it should be a straight line. So I'm drawing free-handed, so but it should be a straight line that passes through 0 or this particular point, or any line that is parallel to this line will be having slope 2. So all the lines that are parallel to this particular line will have slope 1, and lines parallel to this line will be having slope 2. Likewise, any line that passes, if you talk about negative slope, so let's say if you want to draw a slope of -2. So let's erase the things that are not required. So for plotting a slope of -2, it means that you will be having two parts of y at negative side and one part of x. So a line that passes through 0 and this point, a straight line, will be having slope -2, or any line that is parallel to this line anywhere. So if you draw this line parallel to this particular line, so this line will also have slope of -2. So this is how we usually deal with drawing slopes or drawing lines having slopes on normal graph papers. But if you talk about the graph, the semi-log paper, since I told you that it is going to have log scale on x-axis, so you have in the form of decades 1, 10, 100, 1000, and from the gap between 1 and 10 is a decade. Likewise, between 10 and 100 is a decade, and between 100 and 1000 is a decade. And on the y-axis you have linear marking. So if suppose you desire to draw a slope -20 dB per decade, so since this is the dB axis, the magnitude, and you will have to mark, for example, 10 represents 1 centimeter, 20 represents 2 centimeter, 30 represents 3 centimeter, and so on. Then likewise you will be having on the negative axis -10 and -20, and so on. So this means that this 10 represents a dB, 10 dB, this will be 20 dB, and so on. And gap between 1 on x-axis, gap between 1 and 10 represents a decade. So if you take 20 parts of y-axis with the negative sign, since we have negative sign, so we will be talking about 20 parts downward, and 1 decade on x-axis. So 1 decade is this one. So a line that passes through the origin, which is in fact not a 0 for x-axis. So you, in case of the x-axis, will never be having a 0 on x-axis, because you're talking about a log scale. So if you look into the graph that I showed you here on log scale, so you see that 10 raised to the power 0 is 1, which means that you have following this 1, 10, and after this 10 you will be encountering 100. But before this 1 you will be having 0.1, and before 0.1 you will be having 0.001. So you won't be getting any 0 on the x-axis whenever you have the axis represented in the log form. So this is what we mean by having 1 on the x-axis at origin. So this gap is 1 decade. So -20 dB per decade means that you will be drawing a line passing through this particular point and this point. So this line will be having a slope -20 dB per decade. Likewise, if you are interested in drawing +20 dB per decade, So you'll be taking 20 parts of y-axis, which will be passing through 20, and 1 decade on x-axis, and the line passing through this point and this point will be having slope plus 20 dB per decade. Likewise, if you're interested in plotting 40 plus 40 dB per decade, so you're going to take 40 parts on y-axis and 10 part or one decade on x-axis, the line that passes through this origin, and this point will be having slope 40 dB per decade. So if you still face any problem in identifying the slope in terms of dB per decade, you can post questions on Classroom or you can send me an email on this email ID. Now moving on further. So the phase of this system is, now we obtain the magnitude till now, which was the second step while we perform frequency domain analysis. Now if we talk about the phase, so in order to obtain phase, we have, if you look into the function, so Gj omega is 1 upon j omega. We are interested in finding the phase of this function. So the same thing that you learned in phasor form, you can write this as 1 plus j0 divided by 0 plus j omega. So this will give you the angle from numerator will be tan inverse 0 upon 1, which is 0, and in the denominator you will be having tan inverse omega upon 0, which is 90 degrees. Now if you're going to take the angle corresponding to the denominator, if you talk about the angle that this denominator will be contributing, will be negative. So all the angles in the denominator will be contributing a negative angle, while the angles or the expressions on the numerator will be contributing positive angle. So coming back to the same question. So the phase of the system is tan inverse tan phi, which is minus 1 upon omega upon 0. So I told you phi inverse will be minus of 1 upon omega by 0, and this will be giving you an angle of this expression is minus infinity, and phi will be equal to tan inverse of minus infinity. That will give you minus 90 degrees for all frequencies. So now if you try to plot this on the Bode plot on the semi-log paper, so we identified the slope of the line, which is minus 20 dB per decade. So the slope of this line is minus 20 dB per decade. In other words, we computed values for omega 1, for omega 10, and omega 100. So for omega 1, we saw that dB was 0. For omega 10, we saw dB was minus 20, and for omega 100, we have dB as minus 40. So we are going to have a straight line with slope minus 20 dB per decade, and that will be drawn by identifying the points, since you can identify only one point and the slope, so that will be enough to draw the line, the magnitude plot. Now for obtaining the phase, we obtain the expression, and we saw that phase angle is always minus 90 for any value of frequency. So there is no change in the phase angle if the frequency is changed, and thus you will be having the angle minus 90 degree plotted as phase. So this represents the Bode plot of Gs equal to 1 by S. So I guess this makes clear to all, and if you have questions and doubt, you can ask me.